That's my pleasure to introduce Michael Bate. He's going to speak about simple models for algebraic groups.
Yeah, so follow that. Thank you very much for the invitation. It's really is an honor to be here in such a famous place, such a distinguished audience. I hope I can provide you something in the spirit of what we've just seen. So, well, we will see. So I should say straight away, all of this is joint work with David Stewart, who is at Manchester now. And yeah, I want to talk to you about representation theory of algebraic groups, so I should start by setting up some notation. So let's have a field. And I want to talk about smooth connected linear affine algebraic groups over this field, and I want to talk about the rational representations of such groups. So linear actions of such groups on k-vector spaces with a morphic structure. And the first observation is, if you're interested in the simple modules, which is what I want to tell you about, because such a group acts locally finitely, the simple modules will be finite dimensional. So the simple modules, the simple rational modules, are finite dimensional. So if I had put some restrictions on my field, say I had said it was an algebraically closed field, or even a perfect field, the next thing you would do is factor out the unipotent radical of your group and then start talking about reductive groups, right? But as we saw in the last talk this morning, there are problems in doing that, specifically over imperfect fields. You might not be able to see the full unipotent radical. So the best we can do is reduce to a question about pseudo-reductive groups. So G will act on its simple modules through a quotient and the best I can do is quotient out by as much of the unipotent radical as I can see over K. So maximal connected normal unipotent subgroup over K. And these guys, then I get a guy with a trivial K unipotent radical. These are the pseudo-reductive groups. Okay, so immediately I have to talk about Tits, which is good, which is appropriate in this conference. So it was really Tits, I believe, I wasn't there, in the 90s in a course in this place somewhere, maybe in this room, I don't know, who first laid out the possibility of some sort of systematic study of pseudo-reductive groups that sort of mirrors what we all know and love for reductive groups. Okay, so this was a course at the college in the 90s, and then this work was picked up in the 2000s by Conrad-Gabber-Prasad in a series of works, who finally managed to produce a classification of pseudo-reductive groups. So there's this classification, and this classification, if you look at it not very carefully or from far enough away, looks very familiar. Okay. There's a root system. There are root groups. It all fits together as you might expect. There's pseudo-parabolic subgroups and all of this stuff. If you look a bit more closely, you see that things are not as simple as that. The root groups are not one-dimensional anymore. But still, it's a very beautiful classification. What else can go wrong? Well, there are some non-reduced root systems showing up. There's some type BC groups showing up. But still, this is an incredible achievement. And as I say, started by Tits in the 90s, picked up by these three. I don't need the full force of this classification, in fact, so I'm not going to give you full details. I'll do a couple of examples later on, maybe, if I've got time. What I need is one of the key results that you see along the way to this classification. And it goes like this. So if, I will define my terms in a second. So if G is so-called pseudo-split, pseudo-reductive. Let me have half of this board. Then it has a Levy subgroup. So that is, what does it mean to be pseudo-split? It means I have a split maximal torus. So i.e., if there is a split maximal torus T inside G, then in fact I can find a reductive subgroup containing T, which is a Levy subgroup. Then we can find a reductive subgroup M containing T such that, well, I need to extend scalars to see the unipotent radical, but once I do, I extend, say, up to the algebraic closure of K, then this group decomposes as a semi-direct product of this reductive piece and its unipotent radical. This is kind of amazing, I think. Somehow when you read the book of Conrad-Gabber-Prasad, the first big one, which has been weighing down my desk for many years now, is somehow well, at least to me, the significance of this escaped me at the time. And then I saw Prasad give a series of talks about this work, and you realize how central this is to the whole ability to produce this classification and do this structure theory. But for us, we want to work with representation theory, and we know representation theory of these guys. I claim we know the representation theory of these guys. Of course, there's many, many open problems about representations of reductive groups, but at least now I have a reductive group to play with, and it is split. Okay, so this is a maximal torus T of G, so it's a maximal torus of M, so I have a split reductive group to play with. So let me remind you what we know about simple modules for reductive groups. This, I think, goes all the way back to Chevrolet. The simple modules for M, the rational simple modules for this reductive group M, corresponds to a system of dominant weights for the maximal torus. Okay, you need to pick a Borel so that you have a partial order, and then you pick the dominant weights. And if I hand you a dominant weight, there's precisely one simple module corresponding to that dominant weight, and the label is the highest weight appearing. Okay, so this is the high weight space here. For the torus is this weight lambda. Okay, and one way to produce these simple modules, if you remember, is to take the one-dimensional module for T of weight lambda, blow it up to a Borel by letting the unipotent radical act trivially, and then induce that up to G. You get some module, and you need to take the socle of that. Okay, here's a theorem due to me and David. So we started thinking about this, and we did some examples, and we thought, well, I wonder what happens if you just naively do this for the group G. So I take the simple module for G, for M, sorry. I haven't given myself enough room. I take the simple module for M. I can induce that from M to G. Now this is not so well behaved, because I'm inducing from a reductive subgroup up to the big group. This might be some big, horrible, infinite dimensional thing in general, but I can still ask what's the socle of this thing. So I'm going to define this object to be LG lambda, and I'm going to tell you that it's a simple module for G. And in fact, this classifies all the simple modules for G. Yes. Yes. So in fact, in this, sorry, I should say I'm concentrating here on this pseudo-split case for now. So there's always a Levy subgroup, and the root system of that Levy subgroup is fixed. So they're not all conjugate, but it's the same group in the abstract. Yeah. Okay. So in fact, very quickly, we have our hands on all the simple modules for G. They are classified by these dominant weights. They are labeled, at least, by these dominant weights. So let me tell you some properties of these, and then I want to spend some time with an example. Okay, so some properties. So as you might hope, first of all, lambda is still the highest weight for the torus. But the weight space for lambda is no longer one-dimensional in general. So what is it? Well, this goes back to something else we saw this morning, in fact. Inside this group G, we can take the centralizer of this torus. Centralizer of our maximal torus is a Cartan subgroup. Then it turns out that this is also a pseudo-reductive group, and it's commutative, as the notation hopefully suggests. So then this is, C is commutative and pseudo-reductive. Right, and it's one of the pieces of this open cell decomposition we saw this morning. And then the high weight space in here, so the lambda weight space in Lg lambda is in fact isomorphic as a module for this Cartan to the simple module for C. Okay. So it's clear, right, that the high weight space is C stable because it's the centralizer of T, and in fact we can identify it as the simple module for this commutative pseudo-reductive group, which is also covered by this theorem. So we know such a thing exists, and it sits at the top of this simple module. Okay, so we're led to consider what these simple modules for commutative pseudo-reductive groups can possibly look like. And this feels like a really hard problem because these guys, commutative pseudo-reductive groups, there's sort of no hope of trying to write all of them down. Okay, so this classification of pseudo-reductive groups is up to really being able to understand commutative ones, and that's a wild problem somehow. Okay, but actually their representations are not as bad as their structure somehow. So I can actually identify this simple module for C in a variety of ways. So let's do it this way first. So if let's let K prime over K be the minimal field of definition for the unipotent radical. Okay, so the full unipotent radical of G is not K defined, but it will descend to some minimal field extension of K. And in fact, you can show that all you need to do, the only obstruction in the way of seeing the unipotent radical is a purely inseparable extension. Okay, so then K prime over K is purely inseparable. And let me just squeeze this. No, let's not squeeze anything. It's bad practice, right? So I have this purely inseparable extension somehow attached to my group G. It comes with the group. And I can see this simple module I'm after for the Cartan inside this extension. And LC lambda identifies with some field E some intermediate extension. So it's somewhere in between K and K prime. I should mention also some work of Brion related to this, coming from a completely different angle, where he wrote down representations of commutative algebraic groups. I saw a talk that Brion gave in Bonn about this, and as he said, it feels like a strange thing to do to begin with, to be worrying yourself so much about representations of abelian groups, but in this case, there really is something to say, and it's non-trivial. So, if you don't like this, which is still not particularly precise, even better, we can identify this field as the endomorphisms of the simple module. Okay, so it really is sort of intrinsic to the whole thing. Okay, very good. So what about the structure of the simple module LG lambda itself? Well, we got it by inducing from this Levy subgroup M. So one natural question to ask is what happens if you restrict back down? So this is actually very nice and very well controlled. What you get if you take the simple module for G and restrict back down to the Levy subgroup is just a bunch of copies of the thing you first thought of. And how many copies? Well, the weight space is here. The high weight space is one-dimensional for M. So we have exactly the degree of this extension, or in other words, the dimension of the simple module for C copies of this simple module. So we get a dimension formula out of this observation. So the dimension of LG lambda is the dimension of LM lambda times the dimension of the simple module for the Cartan. Okay, so in some sense, this generalization to pseudo-reductive groups tells you that in order to understand the representation theory of algebraic groups, all you need to do is understand the representation theory of reductive groups and these commutative guys. And these commutative guys are not so bad. Their representations are fields, at least in this pseudo-split case. Okay. So one final thing before I give you an example. So this last thing I wrote down, this decomposition of what happens when you restrict to M, sort of tells you that this simple module is kind of made up of a bunch of copies of the simple module for the Levy glued together in some way. And if you want to see exactly how they're glued together, you can, but only if you're willing to base change up to this extension E. Once you do this, so this has structure in some sense controlled. Well, it's controlled by the high weight space. So as a ring, the high weight space is, well, I started off with E, and then I tense it up with E. So I get this strange beast, this tensor product of two inseparable extensions over the field K. This is a local ring. There's an obvious map to E that just takes tensors and multiplies across the tensor. It's a local ring, and it's got a large maximal ideal inside it, which is nilpotent. Okay, so we have the maximal ideal, let's call it M, which, well, if you think about it, it's generated by differences between one tensor x's and x tensor 1's. Those are the sorts of elements that get sent to 1 by this quotient map. And this is nilpotent, this ideal, because if I raise to a sufficiently high power, the x's, a sufficiently high p power, the x to the p to the whatever it is can be pulled across, and I get 0. Okay, so this is a nilpotent maximal ideal. And I have a filtration of this ring by powers of this maximal ideal. So I've got I've got m squared. I've got this m-adic filtration. And this m-adic filtration gives a corresponding filtration of this module. And you can see all the sections of this module somehow in this filtration. Okay? So again, with the example, this might become clear. Okay, so the m-adic filtration somehow controls how the LM, these LMs are glued together. Okay, good. Right, so let's do an example. I think this is a sensible thing to do at roughly half time. So I want to do the first example that I worked out, which we somehow made us realize that something might be possible, which is to do type A1. Okay. In particular, because we know what simple modules for SL2 look like, at least really concretely, so you can sort of get started. So first of all, I need to produce for you a pseudo-reductive group, not a reductive group of this type. And the main machine for producing pseudo-reductive groups is Bate restriction. So again, we saw this morning. I might give just a couple more details. So this is a restriction of scalars operation, so I need a field extension. So let's just have a field extension k prime over k. Let's say it's finite. Then Bate restriction should take in groups over the big field and spit out groups over the small field. So if I have a k prime group g prime, say, it's easiest to write down if we think of this functorially. So we think of this as a functor that takes in k prime algebras and spits out groups. Then I can tell you what the Bate restriction, let's call it G, does by telling you what it does to a K algebra. It's supposed to be a K group, so I should be able to plug in a K algebra. Let's call it A. So I have a K prime group G prime. I just need to turn my K algebra A into a K prime algebra, and I do that with the tensor product, right? This is sort of functorial. It's the only thing you can do, really. Okay, so this is for K algebras A. Okay, and if I start with a smooth connected affine K prime group, I end up with a smooth connected affine K group. This is not obvious from this characterization of the Bate restriction, but it is true. And the point for us is, the main point for the production of pseudo-reductive groups is if it happens that K prime over K is purely inseparable, of finite degree, and G prime is reductive, then G is pseudo-reductive, but not reductive. Okay. So this process of Bate restriction, which looks totally different for separable extensions. For inseparable extensions, it accepts reductive groups and spits out pseudo-reductive groups. And this is kind of the main tool in this classification result of Conrad-Gabber-Prasad. Yeah. Yes, I'm assuming those things. Yeah, so it's a non-trivial extension, and I'm starting with a non-identity group. Yeah. Okay, so let's do this for the case that G prime is SL2 over K prime. So I want to try to convince you that this group is pseudo-reductive. So one way to do that, this is not a proof, but it's a sort of hand-wavy heuristic, is to just look at some of the points. So if we look at the points of G, that's G is going to be this Bay restriction, and K prime over K is positive degree inseparable. What are the K points of G? Well, according to my recipe, I take K and I tensor it up with K prime. That just gives me K prime, and I plug it in to G prime. So I get a copy of SL2, but over the bigger field. This is somehow the point of Bay restriction, right? You look at the group over the bigger field as a group over the smaller field. So the point is that this, on the level of K points, looks like a reductive group. Okay, it's over the wrong field, but it still looks like a reductive group. It doesn't have any normal unipotent subgroups inside the K points. But if I plug in instead the field at the top end and look at G of K prime, then I get SL2, and I have to tensor K prime up with itself over K, and I get one of these rings again. I get one of these guys. The purely inseparable extension tensored with itself over K. So I can reduce modulo the maximal ideal. I get a map reduction modulo this maximal ideal that's sitting in here. Just take the matrices and reduce all the entries. And the kernel of that is some massive normal unipotent subgroup. Right? This is a nilpotent ideal. So 1 plus the elements in here is going to be unipotent guys. So the kernel is unipotent. Sorry, I didn't.
You assume K prime of K is
Purely inseparable, thank you. Yeah. Yes. Yes, I don't want any separability in the way. Yeah, thank you. So there is a unipotent, there's a normal unipotent subgroup hiding in here somewhere. Okay, and you can soup this up to find the unipotent radical properly. But hopefully this is convincing that there is something unipotent and normal hiding in here somewhere. And maybe a picture of what's going on is helpful as well. So what's really happening, and this is the sort of picture you get in this classification. If I draw the A1 root system, then the group G prime, SL2 over the field K prime, is kind of made up from, well, there's the torus in the middle, which is just a copy of the multiplicative group. And then on each root, I've got an additive group, right? And then what happens when I Weyer restrict to get G is that each of these blows up, because I'm just taking the Weyer restriction of each of these. But I get the same root system. I still get the A1 root system. But now sitting in the middle here is this cartan, which is the Weyer restriction of the GM. Okay, another group we saw this morning. This is the guy when you quotient out by the GM, you get this nasty wound thing. And then on each root, I've got a nice split unipotent group. I've got just the Weyer restriction of GA. So this is just a copy of affine space, but of dimension, the degree of the extension. Okay, so the dimension of all these one-dimensional pieces blows up to the degree of K prime over K, but I still have a root system. So in this is very typical of what you see for these pseudo-reductive groups. Okay. So what about the representations of this gadget G? So we're expecting from the theorem here's a point. I'm in France, aren't I? So the natural numbers include 0. Am I right? Am I right? It's this Bourbaki convention. So we know that the representations, the simple modules, let's be safe, simple modules for G should be labelled by dominant weights for the torus, so that is non-negative integers. So the first thing I want to do is think about what the representations for this cartan should be, corresponding to each non-negative integer. So for C, which is the Weyl restriction of a Gm, we can get quite a long way by looking at the k points, in fact. So I'm just Weyl restricting the multiplicative group from k prime to k. So the k points of this Weyl restriction is just the field k prime, throw away 0 under multiplication, right? So let's take an integer lambda, and let's write lambda. I want to pull out all the powers of p that divide lambda. So I'm going to take, let's say, p to the a for some a times lambda prime, where p does not divide lambda prime. And think about what happens when I apply the map from this field to itself, which is just taking elements and raising them to the power lambda. So if I've got any powers of p dividing lambda, this is actually it's going to end up in here, but it's actually going to end up in a smaller field. It's going to get knocked down by however many p's I've got. Okay, so that actually ends up giving what's the simple module going to be? Well, as a vector space, it is the field extension of k I get by taking all the p to the 8th powers of k prime, and then I need to make it into a k space again, so I need to chuck in k. So this is the extension you get for this cartan. Okay. And it's happening very, very naturally once you know what the representations are. Just got this weight, and it really is raising to that power, and it just knocks me down into this subfield. Okay? So what you see for the group G then, so let LG lambda, well, I won't say so, I'll say in fact. Once you know this, you can identify LG lambda let's give this field a name. Let's call it K lambda to stop too much notation. This representation then can be identified, well, certainly as a vector space, but actually more strongly than that. I take a Weyl restriction, but now I start, rather than starting all the way up at K prime, I start at this intermediate field, K lambda, I Weyl restrict to K, and I look at the corresponding simple module for G prime. Okay, let's write SL2 lambda. So SL2 over K lambda. So this is a vector space of the correct dimension, because it's got this simple module appearing K lambda over K times, essentially. But actually, you can identify this simple module LG lambda with this space in a rather more concrete way, but I won't say that now. Let me just do the smallest example to convince you that this is straightforward. So what if we're in characteristic 2 and the degree of the extension is 2? P equals 2, and I just Weyl restrict from purely inseparable extension of degree 2. Okay, then when lambda is odd, the module for G I'm going to get is just the Weil restriction of the module for SL2 for G. Let's just write LG prime. Now I can write LG prime. Okay. Of course, because Weil restriction is functorial in all the right ways, certainly if I start with a module for G prime and Weil restrict it, I get a module for G. Okay? The point of all of this is that's not always the simple module. It is when lambda's odd, but when lambda's even, actually LG lambda, because I'm sort of factoring through Frobenius, I'm squaring everything, I'm knocking the field down to k, I just get this module over k, right? The simple module over k for SL2. Okay, so I get something of half the dimension of the Weil restriction in this case. Okay. And just this last point about what happens if I then extend scalars back up. So in the first case, if I take this simple module, LG lambda, and I extend back up to the extension k prime. Remember I said this is sort of how you can see how the various pieces are glued together. What you get, you see the full unipotent radical over k prime. So what you get is a copy of the simple module of high weight lambda sort of over the top of itself. And the unipotent radical is gluing these together in a tower. So there's a simple socle, there's a simple head, and they're glued together, but this is not a semi-simple module. Yeah, so this is meant to indicate that there's a submodule like this, and then the quotient is this guy, yeah? Yeah. I'm sorry. Somebody taught me this once. I will never use it again. Okay, very good. Right. So I still have some time. This is very good. So this was all the under the assumption that we have a split maximal torus. Okay. And as Zev said in his talk this morning, somehow the problem, if you don't, is a bit easier to handle because that can be solved by separable extensions. And the same holds in this case. So let's just do the general case. So this, again, is following Tits, I should say. So there's a paper of Tits from, I think, 1971 in Kreller's journal where he describes what to do for reductive groups over an arbitrary field and how to look at the simple modules for reductive groups over an arbitrary field. I don't think this is so well known. I must admit I found it quite hard to read, but the basic idea is extremely simple. Right, so if I start with a T inside a G, pseudo-reductive, okay, because I've already reduced to this case without any assumptions on the torus. If T is not split, well, I can fix that by a separable extension. And in fact, let's take a Galois extension so that we have a Galois group to play with, some finite Galois extension. What shall I call it? Omega maybe over K, such that T omega is split over omega, right? So then the group G, when I base change to omega, G omega, is now a pseudo-split, pseudo-reductive group. It has a split maximal torus in it, and I know how to label the simple modules for that group. The question is, how can I use that to label the simple modules for G? And the answer is very straightforward. Let me just get it right. Yeah, okay. So then the simple G modules are just labeled by, rather than by single weights, they're labeled by Galois orbits, gamma orbits, in the dominant weights for this torus T omega, where gamma is the Galois group. Okay, so you can make the Galois group act because T omega, it's the base change of a torus over K, so it has a descent to K, so I can make the Galois group act on the weights for T, and then I can even turn that into an action on the dominant weights once I've chosen a positive system of roots. So there really is a Galois action on the dominant weights for this torus T, and I just get a labeling of the simple modules for G by the orbits of the Galois group. Yeah. Yeah, so you take the natural action on the weights, and then there's a unique element of the Weyl group that will take you back into the dominant chamber, and you do that. This is well defined. Okay. And what do the simple modules look like? Well, if we take some orbit, suppose it has length r, is such an orbit, then if I take the simple module corresponding to that orbit for G, and I go all the way up to omega, you get what probably many of you expect. You get a bunch of simple modules corresponding to the orbit, direct sum together. You can't quite get everything you hope for. It's not always going to be that they appear with multiplicity 1, but they all appear with the same multiplicity, some common multiplicity d, okay, for some d. So that's what the simple modules look like. And yeah, the final thing I wanted to say really is that if you're a bit more careful, so I didn't really take any care about this extension I picked. I just wanted to split the torus somehow and have a Galois group to play with. If I take a bit more care, you can actually show that there exists a nice tower of extensions. So some, let's call it F over, let's say, L over K, with L over K separable, F over L purely inseparable, such that you can also describe the endomorphisms of this simple module, such that if you take the endomorphism ring of this simple module LG gamma dot lambda, what you get, well, what you get up here, you're going to get a bunch of matrix algebras corresponding to just sending these guys to themselves, and that's what you get. You get D by D matrices with entries in this purely inseparable extension. Oh, sorry, I missed off an important thing. So I take the endomorphism ring, I want to see its structure, so I do need to base change up to L. Once I've done that, I can see them as a direct sum of matrix algebras over this inseparable extension F, and there are this many of them, R of them, right? So they're all, that's how the simple module can be mapped to itself. Good. I think I'm done, so I will stop.